name is Caroline.
And I'm Rachel.
We're biomedical engineering students here at the University of Delaware.
Today, we will be talking about projectile motion.
Projectile motion can be seen in many examples in the real world. Analysis of this type of motion can help improve performance and increase accuracy.
To make this a little interesting, we will be using the green arrow, a DC Universe superhero, in order to help introduce the concept and the corresponding equations.
Let's look at the green arrow as he is shooting an arrow from his bow. In this picture, he is shooting it with some velocity v at an angle from the horizontal.
His arrow will follow the path indicated in red as it flies from his bow and is launched at his target. If you pause and take snapshots of the arrow as it flies along the path, you can see that the velocity changes in both direction and magnitude. But why does the path of the arrow curve down?
In order to see what's going on and why this happens, let's split up the velocity into its x and y components. As you can see, the velocity in the x direction stays constant over the flight in both magnitude and direction, while the velocity in the y direction changes in both magnitude and direction. Why do they act differently?
Well, the y direction has the force of gravity opposing motion, causing the arrow's y velocity to slow down during the flight. Therefore, the y velocity decreases until it reaches 0 at the peak of the flight and then increases, but in the negative direction, until the arrow hits the target. This change in the y velocity is what causes the arrow to curve down.
Therefore, the following equations can be used to describe the motion of the arrow in the y direction. The first allows you to solve for the height, or y position, of the arrow at a given time. The second allows you to solve for the arrow's velocity in the y direction at a given time.
So what about the x direction? Why doesn't the x velocity change throughout the flight of the arrow like the y velocity? Is there a force acting on the arrow in the x direction? No, there is not. Since the arrow is slim, any possible drag caused by the air is negligible.
The equations used to find the x distance the arrow has traveled and its x velocity are very similar to those used for the y direction, except since there is no accelerating force, the last term of each equation is removed.
Now that you've been introduced to the concept of projectile motion, let's do an activity to demonstrate how changing different variables, such as angle and initial velocity, alter the path of a projectile. Since neither of us are expert marksmen, we are demonstrating with slingshots instead of bows and arrows. While we did this demo inside, we recommend doing this activity outside as the projectiles can fly pretty high and far. For this demo, we marked 1-foot distance lines on a table in order to see the relative distance the projectile is launched. The first 2 launches Rachael performs have different launching angles, but she keeps the amount she pulls the slingshot back constant. This is to show the effect the initial angle has on the projectile's path. For this launch, Rachael has the projectile at a relatively horizontal angle. As a result, the projectile only flies about 1.5 feet. But for this next launch, Rachael increases the angle and pulls the projectile back at about a 45-degree angle. You can see that this resulted in a projectile flying around 2 feet, 1/2 foot farther than before. For this third launch, we will compare it to the 45-degree launch in order to show how pulling back more on the slingshot, but keeping the angle constant, alters the flight trajectory. As you can see, by pulling back more, the velocity increases and more distance is covered. While the green arrow doesn't plug and chug through the projectile motion equations, he does analyze each shot in the seconds before he takes it. To make sure his arrow strikes his foe, he thinks about how far the arrow has to fly, at what angle he should make the shot, and how far he'll have to pull back on his bowstring to obtain the required velocity. Through much practice, all of this has become instinct, allowing the Emerald Archer to rapidly shoot arrows and ultimately save the day.